Introduction. Why next-gen computing? CMOS technology is reaching physical and economic limits, with transistor scaling no longer providing the same improvements in speed, power efficiency, and cost. The report emphasizes that next-generation computing models are being explored to overcome these bottlenecks and to enable new capabilities in fields like robotics, AI, defense systems, and scientific computing. These technologies shift away from charge-based electronics and instead explore biological, magnetic, quantum, optical, and nanoscale mechanisms for computation. End of CMOS scaling. Moore's law has slowed as leakage currents, heat dissipation, variability, and fabrication cost sharply increase. Emerging technologies must solve challenges such as scalability, switching speed, energy efficiency, device reliability, and compatibility with system architectures. The report states that no single dominant successor exists yet, so multiple paradigms are being researched simultaneously. Overview of four major domains. The report focuses on four promising domains: biocomputing, nanocomputing, spintronics, and optical/photonic computing. Each domain approaches computation using fundamentally different physical principles. While quantum computing is prominent, the report intentionally excludes it to highlight lesser known technologies that may complement or compete with CMOS in the future. Biocomputing overview. Biocomputing uses biological processes or structures as computational systems. The field includes DNA computing, membrane (P system) computing, neuromorphic computing, neurocomputing, and molecular information processing. Biological systems are inherently parallel, adaptive, and energy efficient, offering models for powerful, non-traditional computation. Biocomputing, DNA and molecular computing. DNA computing stores information in nucleotide sequences and processes it using chemical reactions. A test tube can contain trillions of DNA molecules, enabling extreme parallelism. Advantages include massive parallel search, low energy requirements, and extremely dense information storage. Challenges include high error rates, slow reaction cycles, and limited programmability, although research continues to improve reliability and assembly techniques. Membrane computing and P systems. P systems model computation using the structure of biological cells, where membranes define regions and evolution rules specify how objects interact. This creates inherently parallel, distributed models capable of solving complex problems efficiently. Variants include cell-like, tissue-like, and neural-like P systems. Applications span bioinformatics, cryptography, modeling immune responses, and solving NP-hard problems. Neuromorphic computing concept. Neuromorphic computing designs hardware that mimics brain structure and signaling. Instead of binary voltage levels, neuromorphic chips use spikes, plastic synapses, and parallel network architectures. Computation and memory coexist in the same physical units, reducing bottleneck found in von Neumann architectures. Memristors are a key enabling device for synaptic modeling. Neuromorphic hardware examples. Major neuromorphic platforms include IBM TrueNorth, Stanford NeuroGrid, Manchester Spinnaker, and the EU BrainScales project. These systems aim to achieve high efficiency, low power, and fault-tolerant computation. Industrial challenges include scalability, interconnect density, variable in device behavior, and manufacturing complexity. Biocomputing summary. Biocomputing offers highly parallel adaptive computation inspired by biology. DNA computing and membrane computing provide theoretical breakthroughs, while neuromorphic systems are rapidly maturing towards practical hardware. However, biocomputing remains complementary to traditional architectures and faces challenges in programmability, reliability, and large-scale integration. Nanocomputing overview. Nanocomputing explores computation using nanoscale devices such as quantum dots, nanomagnets, nanowires, and molecular switches. These devices attempt to overcome CMOS scaling limits by using new state variables, electron position, magnetic orientation, or quantum confinement. The report highlights quantum dot cellular automata, QCA, and nanomagnetic logic as leading approaches. Quantum dot cellular automata, the QCA. QCA represents bits not as electrical currents but as electron arrangements within nanoscale quantum dots. Logical states correspond to stable electron configurations. QCA logic gates require extremely low power and may support dense, regular layouts. Challenges include achieving stable, manufacturable structures and managing coherence, metastability, wire crossing, and clocking. Nanomagnetic logic, NML. NML uses nanoscale magnets whose magnetic orientation represents binary states. Information propagates through magnet interactions rather than current flow, enabling ultra-low power, non-volatile logic. Advantages include high density and inherent pipelining. Remaining challenges include thermal noise, fabrication imperfections, slow switching speeds, and development of on-chip clocking mechanisms. Nanocomputing research landscape. Research institutions in the US and Europe dominate nanocomputing publications. Collaboration often occurs around nanomagnetic logic and QCA. The technology remains early stage but shows promise for complementing CMOS in specialized, low-power architectures and emerging memory applications. Spintronics overview. Spintronics uses electron spin and its associated magnetic moment to process and store information. Devices rely on magnetic tunnel junctions, MTJs, spin transfer torque, STTs, and spin orbit interactions. Spin-based devices are non-volatile, energy efficient, and compatible with dense memory applications. Spintronics devices, MTJ and STT. Magnetic tunnel junctions consist of two ferromagnetic layers separated by an insulator. Their resistance depends on magnetic alignment. Spin transfer, torque, allows switching magnetization using polarized current instead of large magnetic fields. STT-MRAM is a leading next-generation memory due to speed, endurance, and low power. Spin-based logic and spin qubits. Beyond memory, Spintronics enables logic devices using spin waves, spin transistors, and spin-based majority gates. Spin qubits also serve as a platform for quantum information. Challenges include thermal stability, variability, error rates, and integrating magnetic materials with CMOS fabrication processes. Spintronics research trends. Spintronics is the only one of the 4 domains experiencing growing publication trends. Major institutions include Purdue University, CNRS, University of New South Wales, and collaborations with industries such as Intel. Interest is driven by STT-MRAM commercialization and the potential for future spin-based logic. Optical/photonic computing overview. Optical computing uses photons instead of electrons to process information. Photons travel faster, dissipate less heat, and enable massive bandwidth. Silicon photonics, reversible logic, photonic integrated circuits, and optical quantum computing are central research topics. These technologies offer extremely high-speed communication and parallelism. Photonic logic and integrated circuits. Photonic chips use lasers, waveguides, modulators, and detectors to perform logic operations and routing. Optical interconnects offer higher bandwidth and lower latency than copper wires. Challenges include integration, density, energy-efficient light sources, noise, fabrication cost, and interfacing optical electronic systems. Optical photonic research landscape. Research leadership includes Chinese Academy of Sciences, CNRS, and University of Oxford. Collaboration networks connect major institutions across Europe, China, and the US and Australia. Applications include high-speed data processing, telecommunications, and quantum photonics. Conclusion. Next-generation computing will likely be heterogeneous. Biocomputing, nanocomputing, spintronics, and optical computing each address specific limitations of CMOS. While none are ready for full replacement, they offer strong potential as complementary architectures. Continued monitoring Research investment and cross-disciplinary collaboration will be essential as computing moves beyond Moore's law.
Okay, Professor, today we're going to be talking about quantum computing from spintronics and optical photonic computing and DNA computing from biocomputing. The main reason why I'm choosing these two topics today is because I realize they're really revolutionary when it comes to the way we handle certain things, quantum computing, such as storage or like things that computers that can connect with each other in a way that only a singular one can, but instead of a singular one this time, we're talking about from two different places. And for DNA computing, the way we storage and manage our DNA, I should say, or things that have to do with illnesses or things of that sort, I should say. That's the main reason why that I picked these two topics because it helps us, and whether it comes to like science or everyday life, I should say. So the article that I chose for quantum computing is from Wang TJ and Wang C, Parallel Quantum Computing Teleportation for Spin Qubits and Quantum Dot and Microcavity Coupled System. Now the goal about this is basically to make a non-local parallel quantum computing system. So they're just trying to see whether it's possible to build a quantum computer where the parts can work together even if they're not in the same place. Now the key mechanism for this is that it proposes a scheme to perform quantum computation and teleportation among distant physical locations and in parallel. Now, they just want a quantum computer and teleport quantum information between faraway places at the same time. Now, that's the whole point and goal for this research, so it makes things more efficient. Now, the significance of this is that we need quantum machines to talk to each other instantly and work together if we want them to grow and connect into a giant network. And this giant network, the reason why we need it or we want it is because it'll make things a lot faster as opposed to the network that we're using now, like the conventional conventional network. Now, the components that we're working with is going to be a solid state system, which is very key in quantum computing, which also makes sense because solid state things usually run faster and load faster, and a lot of things are more faster in a solid state drive or solid state system as opposed to HDD or HDD. My apologies. Now, the qubit type. So the information carriers are spin qubits, which is our electron spins confined in quantum dots. Now, the solid-state quantum computation is basically a tiny piece of matter that can act like a bit of for a quantum computer. Now, the spin part is the direction it's pointing, which is also used to store information. Another key component is we're going to talk about is the coupling slash bus. Now, it's basically the system uses a microcavity to couple the distant quantum dots. Now, it's the microcavity also serves as a quantum bus, which is an intermediary that allows the spin qubits to interact remotely via photons. And the microcavity, it also works like a bus or wire that carries messages. I guess that's the best way to put it. So it uses photons, which is particles of light, to pass information between them. And the qubits that we're talking about are trapped electrons that are so far apart they can't touch each other directly. And this input resource now we're going to talk about. Now this method heavily relies on hyperentangled photon pairs, like polarization and orbital angular momentum, to enable the parallel operations. So what I'm trying to say is they use special pairs of light particles that are connected in two different ways at once, so the system can do multiple things at the same exact time. And that's very crucial to the quantum computing aspect that we're talking about. All right, so now the key quantum operations. Now we're talking about the quantum teleportation of a gate, which is a core idea of the ability to teleport a quantum gate, specifically the Tafali gate, between three spatially separated electron spin qubits. Now they figured out how to send a quantum command or operation, a command to qubits that are far apart, without physically doing the operation there. It just appears there instantly using quantum teleportation. Now we're going to talk more about the Tafali gate a little right now. So it's also the abbreviation is the CCNOT, which is a universal logic gate in classical and quantum computing. Being able to perform it remotely is vital for general purpose quantum computation. The key quantum operations we also involve with is parallelism. By using the hyperentangled photons, the scheme enables the teleportation of two separate operations, a CNOT gate and a controlled phase gate, simultaneously. So basically what I'm trying to say is they're using those superconnected photon pairs to do two different quantum actions at the same exact time. So now we're going to talk about the technical and scalability advantages. So it's also very compact and scalable, which means the use of quantum dots makes the system potentially scalable and compact, fitting within existing integrated circuit manufacturing techniques. Now what that basically means is it's not gonna use much more different manufacturing techniques that we have as opposed to the ones that we already have now. So it's not going to cause too much of a hassle to make because we already have things that can basically integrate with the manufacturer stuff that we have now. So it's not going to do too much work as opposed to like making it work, if that makes sense. Making it is the hard part. Making it work, we already have everything set up. So it's also very non-local. The method overcomes the challenge of requiring physical proximity for interaction, which is basically the whole thing, which is critical for building a functional quantum computer with millions of qubits. The non-local part is a very big advantage because that's what we're mostly focusing on, because we're trying to look for things to communicate with each other without physically being there, which is like the whole main focus of this whole entire thing. So moving on from quantum computing, we're going to move to DNA computing. Now we're going to talk about the core concepts, which is a DNA computer is a machine that uses DNA to perform calculations rather than traditional silicon and electronic components found in conventional computers. Data storage is also very important. It's a core concept. So this data is stored in the specific sequence of the four DNA bases: adenine, guanine, cytosine, and thymine. A sequence of bases that act as a bit string or a variable. Now, the core concepts, again, we're going to talk about is computation or the algorithm. Now, it's performed using molecular biology tools like enzymes and hybridization to manipulate the DNA strands in a test tube. The reactions represent the logic operations. They're doing computing by mixing DNA in a test tube and letting biological chemicals do the work. Now, that's the key thing. We don't want us to do more work. We want these computers to do the computations for us so it's more accurate and faster by also having the biological chemicals do the work for us too. So these two things are going to be working together as opposed to us basically using our resources, what we can do with our hands, which will take much, much longer. The key advantages is massive parallelism, which basically is saying that a test tube has trillions of DNA pieces, like as I said right here, and all of them work at the same time. So it's just like I said before, a DNA computer can do trillions of calculations at once, which is very important because we want to do multiple calculations at once as opposed to just the way we're doing it now. It's a lot faster, it's more accurate, and it'll help with science and also things that have to do with anything that we're basically needing DNA for, sicknesses, illnesses, anything that's deeply rooted of some sort. High density storage, it's also very incredibly dense and can store far more information than silicon based memory devices in the same physical volume. Basically, just saying that it's going to be more easy to store DNA and it could store way more information than that we are even capable of today, which is very important because, like I said, DNA is very complex and it's really nice to store as much things as you can about that sort of strand, yes. Now, another thing is low energy consumption. So it basically relies on natural biological processes, so that results in low power consumption compared to like the circuits that we're using today, which generate a bunch of heat. And obviously, this is a key advantage when it comes to our environment for both sakes, Earth and humans. It's just a lot better for us that we can be around and just navigate. Now, the applications and future potential of DNA computing is is basically everything that I've listed before. It solves complex problems. You know, it requires a checking of a huge number of potential solutions simultaneously, which is very, very important, such as NP complete problems, which is going to use the traveling salesman problem, and complex code breaking. That's very important too. When it comes to codes, DNA is pretty much very complex, and we're going to definitely need a system, or we're going to use a system eventually that will solve as much things as we can without having to use human error, I should say. Because, if we program a specific computer this way, it will be a lot faster. Such as it's going to be maybe hopefully as fast as like navigating a website, but a website will be like our DNA and our storage, if that makes sense. Where things will be easier to, I guess, access and recognize what it is. And also recognizing what it is also helpful for your molecular diagnosis. Now, it can be used for sophisticated molecular diagnosis and drug targeting within the human body by designing DNA circuits that react only to specific biological markers. So, you can make DNA machines that only respond to certain signs of disease in the body. That's what I'm trying to say. This lets them help. This helps them let detect. Wait, this lets them help detect illnesses or deliver medicine exactly where it's needed, as opposed to what we do now, where we'll deliver some medicine to help detect illnesses and probably have some side effects because that's going to affect other parts of the body that we really don't need to be affecting, if that makes sense. We mostly just want to focus on the medicine wherever you need it to be, as opposed to affecting other parts of your body, which causes these side effects. So it'll definitely help with that. Now, we're going to keep talking more about this. So, future hybrid systems, which will not really replace traditional computers, but it can be integrated to hybrid machines, which could, because you're using silicon for general processing and a DNA coprocessor for computationally difficult tasks, which means it won't replace normal computers, but instead use future machines might use regular computers for most tasks and DNA computers for really hard problems, which will definitely speed up the process, like I said before, because we don't have time for human error for certain situations. And for a situation like this is pretty key. Obviously we're not going to just completely abandon our regular computers right away, because maybe the DNA computers will, I guess, not short circuit, but just get overloaded, especially if you're going to just do it on small tasks. But if you just leave it for the big guys, it'll be good. So our regular computers be like the police officers, the DNA computers could be like the CIA agents. Not even. Okay, we're going to talk about the current challenges of the video. Hear me? We're going to talk about the current challenges of DNA computing, which is going to be the lack of control programmability. And the reason for this is because we're not going to fully rely on DNA computing because it can lead to more error rates or incorrect computations that are higher than electronic computers. Now, eventually, this can definitely be fixed because, programmers every day just working on new things, and we're getting new programmers that precisely hold more languages than some. And, just nowadays, a lot more people are driving towards more computer science. So maybe this can be fixed due to human error, or with us, I should say. Speed is a problem because the speed of a single DNA reaction is currently much slower than a single electronic switching operation. Now, I guess the only way to fix that is to, I guess, align the switching operation with the single DNA reaction, but almost make it seem like it can run a little more faster, if that makes sense. Now, scalability is also another problem. The amount of DNA required to encode the necessary data grows to be impractically large. Now, for that, maybe as time goes on, we could figure out to make the DNA, like the encoding part, a little more smaller than what it is now. So like that it's scalable and that we could actually like have a grasp on it and work more towards. Yes. So yes, Professor, these are the two things that we chose, and they're very interesting when it comes to quantum computing and DNA computing. Obviously, some of them have more challenges than the other, and research will hopefully venture onto a solution down the line, because I personally think these two things are remarkably interesting when it comes to programming and science. It's always good to lead humankind or humans to a more advanced, better state. First to say, I guess. So yes, thank you, Professor. Happy Thanksgiving.